In this section, we're going to start taking a look at other sorts of tests other than the geometric series test for convergence, and then also working with the collapsing series. And so 3 different tests we're going to be working with. One of the most important and also one of the easiest, test for divergence. Another test is going to be something called a P-series test that we're going to look at. And then finally, the integral test. So let's start out with a test for divergence. And let's say for some reason we have an infinite series and we just take the limit of the sequence that comprises the series. If that limit is non-zero, that means that this series is going to diverge. All right. And what that means is if we're not continuously adding 0 as the limit of the sequence approaches infinity, that means that the series is either going to get larger or smaller infinitesimally. And so what we'd like to do is we'd like to be able to keep adding 0 or as close to 0 as possible. So that's going to be our test for divergence. Now note that if for some reason that the limit of the sequence does equal 0, that does not mean necessarily that we can say immediately that the series converges. Okay, so the only thing the test for divergence says is whether or not the series diverges. If for some reason the sequence is equal to 0 as the limit goes towards infinity, then we just have to use another test. Okay, so let's take a look at a few examples of the test for divergence. So we have the series n equals 0 to infinity, n over n plus 1. And I'm going to take the limit as n approaches infinity of n over n plus 1. And to be able to evaluate this limit, we just divide everything by the highest power of n in the denominator, which is just n by itself. So this is lim as n approaches infinity of n over n divided by n over n plus 1 over n, right? Which is the same as the limit as n approaches infinity of 1 over 1 plus 1 over n. The only thing that we can do is apply the limit to 1 over n, and we know that that's going to go towards 0. So now the statement becomes 1 over 1 plus 0, which is equal to 1, which is clearly not equal to 0. And so what we can say is that it indeed diverges, right? In fact, this might be the very first test if you're faced with a series that you're not quite sure of the behavior, and you can't necessarily tell a test immediately. You should probably start with the test for divergence, all right, just because it's one of the easier tests, and also it's usually pretty applicable for series that diverge. A couple more examples. So we have this limit, n equals 2 to infinity of n over ln 2n. And so again, we take the limit as n approaches infinity of n over ln 2n. Now, unfortunately for this one, because we have this sort of transcendental in the denominator, or we're not going to divide by n. But what we could do is we could try direct substitution, and we could notice that eventually this turns into infinity over infinity, which is an indeterminate form, which means we can use L'Hopital's rule for this. So we just apply L'Hopital's rule. And remember, L'Hopital's rule says you take the derivative of the numerator, which in this case is 1, and then the derivative of the denominator, which in this case is going to be 1 over 2n times 2, okay, by our chain rule. Okay. Now the 2's cancel out, and we are left with the limit as n approaches infinity of 1 over n, which is the same as the limit as n approaches infinity of n, which is just going to be infinity, which is clearly not equal to 0. As soon as we see that the limit as the sequence does not approach 0, we can say again that it diverges by the divergence test. Another example is the arctangent of 2n squared divided by 2n squared plus 4. And so once again, we apply the limit to just the sequence, okay, ignoring the series for now. So we have the limit as n approaches infinity of the arctan of 2n squared divided by 2n squared plus 4. I'm going to divide everything by the highest power of n in the denominator, which is n squared. So now we're going to have the limit as n approaches infinity of the arctan of 2n squared divided by n squared divided by 2n squared divided by n squared plus 4 over n squared. We simplify, and noting that all the n squareds are going to cancel out except for the very last one. And so now we have the limit as n approaches infinity of 2 over 2 plus 4 over n squared. And then there's an arctangent in there, excuse me, forgot to copy the arctan, which certainly changes the answer. Of 2 over 2 plus 4 over n squared. And then if we apply the limit to 4 over n squared, we know that that's going to go to 0. So we're left with the arctangent of 2 over 2, which is the arctan of 1. Right? And by this point, we should really know what all of our arctangents, our arcsines are at special values. This is equal to pi fourths. And last time I checked, pi fourths is not the same as 0. And so once again, we can see that the series diverges. All right. So in our next video, we'll take a look at a couple more examples, but these are some of the more elementary types. And realistically, this is just an elementary Calc 1 problem where we evaluate an infinite limit and see whether or not that the limit goes towards 0 or not. And if it doesn't go towards 0, it diverges.